The bisection method is one of the simplest and most reliable root finding algorithms in numerical analysis. It works on any continuous function and is guaranteed to converge as long as you start with a valid bracket. Start with 2 points, a and b, where the function has opposite signs. This guarantees that a root lies somewhere between them. Compute the midpoint m, which equals a plus b divided by 2. Now evaluate the function at m. If f of a and f of m have opposite signs, the root is in the left half, so b moves to m. Otherwise, the root is in the right half and a moves to m. Either way, the bracket width is cut in half. Repeat this and the bracket shrinks by a factor of 2 every single step. Watch the colored bars below the axis. Each iteration, the bracket is cut in half. 5 steps reduce a width of 1 to just 0.03, and the midpoints are already converging on x star at 1.5214. Let us apply this to f of x equals x cubed minus x minus 2, starting with the bracket from 1 to 2. The first midpoint is 1.5 and f of 1.5 is negative 0.125. Since f of a is also negative, the root is in the right half, so a jumps to 1.5. From here, the midpoints keep the right bound at 2 while the left bound climbs. After just 5 steps, the interval is narrow and the root is pinned at 1.5214. Here is the same algorithm written in EES. The function next low takes the current bracket endpoints and returns the new lower bound after one bisection step. Inside the function, the midpoint and function values are computed using the assignment operator, and the conditioner decides which endpoint to keep. Function next high is symmetric. It returns the new upper bound. Notice that if and then are on the same line with the body on the next line, followed by else and end if, each on their own line. In the main body, a duplicate chain calls both functions, repeatedly narrowing the bracket with each index step. Paste all 3 sections into a blank EES window and press F2 to solve. Pause and try it out. Now try a second example, g of x equals x squared minus 2, whose root is the square root of 2. This time, watch both the left and right bounds. At step 1, the midpoint is 1.5 and g of m is positive, so b moves left to 1.5. At step 2, the midpoint is 1.25 and g of m is negative, so now a moves right. Both bounds are closing in on root 2 from both sides. After 6 steps, the midpoint is close to the actual root. The function next low SQ handles the lower bracket update for g of x equals x squared minus 2. Next high skew is the symmetric function for the upper bound. The duplicate chain runs 6 steps starting from the bracket 1 to 2. The variable root exact is set to the square root of 2 for direct comparison. After pressing F2, inspect mid of 6 in the solution window. It should read 1.4141, confirming the method converged correctly. The bisection method. Week 1.